Welcome back to our 3D printing video series. In Day 1, we covered the basics of 3D printing and its historical evolution. Today, in Day 2, we're diving deeper into the different 3D printing technologies that make additive manufacturing so powerful and versatile. From the popular desktop printers to advanced industrial systems, we'll explore how each method works, their advantages, limitations, and where they're used. By the end of this session, you'll have a strong understanding of what separates FDM from SLA, or SLS from SLM, and how to choose the right method for your needs. Let's get started. Additive manufacturing, also known as 3D printing, refers to a family of processes that build objects by adding material layer by layer, as opposed to subtractive methods like milling or drilling, which remove material. All additive processes begin with a digital 3D model usually created in computer-aided design software, which is then sliced into thin horizontal layers. The 3D printer reads each slice and prints it sequentially until the final 3D object is built. What makes additive manufacturing revolutionary is its design freedom. Engineers can create intricate internal features, lattice structures, and lightweight forms that were previously impossible to produce. It supports on-demand manufacturing, rapid iteration, and mass customization. Now, let's take a look at the 7 primary categories of 3D printing technologies, according to ISO/ASTM 52900. Fused deposition modeling, or FDM, is one of the most accessible and widely used 3D printing technologies. It operates by feeding a thermoplastic filament like PLA, ABS, or PTG into a heated nozzle. This filament melts and is deposited in layers along a predefined path. The nozzle moves in the X and Y axis while the build platform moves vertically, building up the object layer by layer. FDM is affordable, user-friendly, and ideal for prototyping, educational purposes, and even functional parts when paired with strong materials like polycarbonate or nylon. However, it does come with limitations, such as visible layer lines, lower resolution, and weaker bonding between layers, which can lead to reduced strength along the Z-axis. Stereolithography, or SLA, is the oldest 3D printing technology and is known for producing highly detailed and smooth-surfaced parts. It uses a vat of liquid photopolymer resin that is selectively cured by a UV laser. The laser traces each cross-section of the part, curing the resin as it moves. After each layer is completed, the build platform shifts to allow fresh resin to flow over it, and the process repeats. SLA is popular in industries requiring fine details, like dental modeling, jewelry, and product prototyping. It offers high precision and smooth surfaces but typically requires support structures and a post-curing step under UV light to enhance mechanical strength. Digital light processing, or DLP, is a close cousin to SLA but uses a projector instead of a laser. DLP projects a whole layer at once using a digital micromirror device, DMD, significantly speeding up the printing process. Each mirror in the DMD corresponds to a pixel in the image, giving DLP prints their characteristic crispness. This makes DLP well suited for fast production of small, highly detailed parts, such as dental aligners, hearing aids, and miniatures. The materials are similar to SLA resins, and the prints also require post-curing and support removal. CLIP, short for Continuous Liquid Interface Production, is an advanced resin-based printing technology developed by Carbon. It uses a combination of light and oxygen to create a continuous curing zone called the dead zone between the resin and the oxygen permeable window. This allows the object to be pulled smoothly out of the resin without stopping layer by layer, leading to extremely fast print speeds and superior mechanical properties. CLIP parts are strong, isotropic, and production-ready. However, this technology is proprietary, requires specialized materials, and is mainly used in high-end manufacturing sectors like automotive, medical devices, and consumer products. Selective laser sintering, or SLS, is a powder bed fusion method that uses a high-powered laser to fuse powdered thermoplastics like nylon. A thin layer of powder is spread over the build platform, and the laser selectively sinters the desired regions. The unsintered powder acts as a support material, enabling the printing of complex geometries without dedicated supports. SLS parts are durable, functional, and have excellent mechanical properties, which makes this method popular in aerospace, automotive, and manufacturing. However, SLS printers are expensive, require careful powder handling, and the prints need post-processing like cleaning and surface finishing. SLM and DMLS are metal powder bed fusion technologies that use high-energy lasers to produce dense, high-performance metal parts. In SLM, the powder is fully melted to create a homogeneous solid, while DMLS fuses particles without fully melting them. Despite this technical difference, the terms are often used interchangeably. These technologies can print parts using titanium, stainless steel, aluminum, and nickel-based alloys. They are essential in aerospace, defense, and medical industries for parts like engine components, implants, and heat exchangers. While powerful, they demand post-processing such as support removal, stress relief, and surface smoothing. Electron beam melting, or EBM, is another metal powder bed fusion method but uses an electron beam in a vacuum chamber instead of a laser. The electron beam melts the metal powder, typically titanium alloys, layer by layer. Preheating the powder reduces internal stresses, making EBM ideal for load-bearing applications like orthopedic implants. EBM offers high build rates and produces parts with exceptional mechanical strength. However, it's limited to conductive materials, requires a vacuum environment, and typically results in rougher surface finishes compared to laser-based systems. Material jetting works similarly to an inkjet printer, but instead of ink, it deposits droplets of photopolymer resin which are instantly cured by UV light. The process can use multiple print heads to jet different materials, enabling full-color, multi-material prints. MJ delivers extremely high resolution and surface quality, making it ideal for presentation models, dental applications, and realistic prototypes. However, the printed parts are often brittle and require support structures, which must be removed manually. Binder jetting involves selectively depositing a binding agent onto a bed of powder such as sand, ceramics, or metals to bond particles together. Unlike other powder bed processes, it doesn't use heat during printing. After printing, the green part is sintered or infiltrated with another material to achieve strength. Binder jetting is scalable, fast, and capable of producing large parts. It's used for full-color prototypes, sand casting molds, and low-cost metal components. However, mechanical properties rely heavily on post-processing, and shrinkage can occur during sintering. Sheet lamination is a method where sheets of material like paper, plastic, or metal are bonded together layer by layer. In laminated object manufacturing, LOM, a laser or knife cuts the shape of each layer, and heat and pressure bond it to the previous one. In ultrasonic additive manufacturing, UAM, thin metal sheets are ultrasonically welded together. This method is relatively fast and low cost, and UAM enables embedding of sensors or electronics between layers. However, it has limited resolution and is mainly suited for visual models or specific research applications. Let's compare some key 3D printing technologies. FDM, budget-friendly and easy to use, but with lower resolution. SLA, DLP, clip, offer fine details and smooth finishes, ideal for dental and visual prototypes. SLS, strong, functional parts without the need for support structures. SLM, DMLS, EBM, best for metal parts with excellent strength and durability. MJ and binder jetting, great for color prints or production scale parts but need post-processing. 3D printing offers a host of advantages, including rapid prototyping, on-demand production, reduced material waste, and the ability to produce complex geometries with minimal tooling. It allows mass customization and can dramatically shorten product development cycles. It's a perfect solution for agile manufacturing environments. Despite its many benefits, 3D printing has its limitations. Print speeds can be slow, especially for large objects. Many parts require significant post-processing. Material options, while growing, are still limited compared to traditional methods. Also, surface finishes may not meet final product standards without polishing or coating. 3D printing has found applications across various industries. In aerospace, lightweight parts and customized brackets. In medical, patient-specific implants and surgical guides. In automotive, prototypes, fixtures, and end-use parts. In consumer products, custom wearables and gadgets. In education and research, learning tools and experimental setups. Thanks for joining us for day 2 of our 3D printing journey. Now that you've seen an overview of key 3D printing technologies, get ready to explore each one in detail. Don't forget to like, share, and subscribe. In day 3, we'll begin with FDM technology. See you there.